So, let us do some more problems on central forces, and the first problem is here. A particle is subjected to a central force F r r cap. This is the definition of central force. Define u equal to 1 by r and find the differential equation of the path of the particle in terms of u and its derivative. So, we had obtained path of the particle, especially for the attractive inverse square force, and that was r as a function of theta. So, when you give the relation between the coordinates, you get the path. Here you are asked to work not in r, but in u, which is 1 by r, and then find the differential equation of the path. Means u as a function of theta will give me the path, but what we need here is differential equation in terms of u, du d theta, d2u d theta square, and so on. So, let us start with it. We know that the radial acceleration is a r, which is r double dot and minus r theta dot square, that is this, and this is the force divided by mass. Force is equal to mass into acceleration. It is a central force. So, the entire force is in the radial direction, and therefore, radial acceleration is just force divided by mass. Now, we start from here. What is this r double dot, what is this theta dot, and so on. And you know that for central motion, a constant of motion is angular momentum, which is mass, and then of course, the mass of the particle is m. So, m r square theta dot, and from here you can write what is theta dot. Theta dot is L by m r square, and that is L by m u square in the numerator, because 1 by r is u. So, this theta dot we will write from here, r double dot. Okay. So, r is equal to 1 by u. So, r dot dr dt, r dot will be minus 1 by u square, that is differentiation with respect to u, and then du d theta, because u is a function of theta. So, du d theta, and then differentiation of theta with respect to time. Ultimately, this is dr dt. So, you have to differentiate in terms of time, with respect to time. So, it is this and then theta dot, and that you can write minus 1 by u square du d theta, and theta dot is L u square by m. So, L u square by m, and this u square cancels with this u square, and you have minus L by m du d theta. So, that is the advantage of working in u. You get simpler things like this cancel out and so on. It will be clear further. And then r double dot, we need r double dot. So, r double dot means we have to differentiate this thing with respect to time, and that will be minus L by m d2 u d theta square, and then theta dot, differentiation with respect to theta, and then differentiation of theta with respect to time, that gives me the time derivative of this r dot, which is r double dot. So, let us put these things in this equation here. So, r double dot is minus L by m d2 u d theta square, and then theta dot. In fact, I can write this theta dot from here itself. This is equal to minus L by m d2 u d theta square, and theta dot is L u square. So, this is L here, u square here, and divided by m. So, m here, and that same thing comes here, L u square by m. This is what? This is what I am writing this equation A r double dot, only this part is here, r double dot is minus L by m d2u d theta square L u square by m, then minus r, this r is 1 by u, and then theta dot square, theta dot square is L square u4, so L square u4 and divided by m square, and that is equal to force, this function r, function of r, f at r, this is the force. We will write it as f of u, this will be f in terms of u divided by mass. Okay. Now, this functional form is somewhat different if you write in terms of r, if you write in terms of u. For example, if f r is 1 by r square, then f u that I am writing there is r is u square. So, I am writing this r as 1 by u and it becomes u square. So, in principle this is a different function and this is a different function. This is a square and this is 1 by square. So, in principle I should have written some other symbol here, but I will continue with this and you understand what I mean. This functional form which is given in terms of r, so that has to be just converted into u and that I will be writing there. Okay. So, let us see what it is. So, you have this u and here fourth power becomes third power, and this thing I want to separate out. So, first let me do some simplification. This is d2u d theta square, and let me put plus sign here and minus sign here. Okay. Then it is L square, so L square, and then I have u square, so u square divided by m square, so m square here, plus L square and divided by m square here, and u to the power 3, so u to the power 3, and this is minus f u divided by m. So, divide by this quantity, and this quantity is common here and here except for this u here. Here you have u square, here you have u cube. So, if I take that as common, L square u square by m square and then bracket d2u d theta square and plus u from here, and that is equal to minus f of u divided by m. And take this quantity on the right hand side. So, you have d2u d theta square plus u is equal to this quantity goes to the right hand side, m square divided by in fact 1 m I can cancel out from here itself, this power m square. So, it is just 1 m, I can write 1 m here, and then divided by L square u square. So, L square and u square, and that is it, f u, and this minus sign here. Okay. So, d2u d theta square plus u is equal to minus of f u. So, minus of f u multiplied by m divided by L square u square. So, this is the differential equation. This is that differential equation which we are looking for. This functional form of force, whatever is given, is here. L is a constant of motion for that entire path, entire motion. So, it is here. Mass of the particle is known, and then you have u square, you have derivative of u. So, this is that differential equation. If you think of that inverse square attractive force that we had been talking, then this f of r is minus k by r square, and therefore f of u I will be writing minus k u square, and if you put it there, your equation will be d2u d theta square plus u equal to, in place of this fu you write minus k u square. So, what happens? This minus and this minus will become plus, and then you have to write k u square. So, u square will cancel, k will be there. So, it will be mk by L square. It will be mk by L square, and if you define u prime is equal to u minus mk by L square, if you define another quantity u prime, this is just a constant, because angular momentum is constant in the entire motion. So, it is u minus mk by L square. So, d2 u prime and d theta square is equal to d2 u d theta square, and then this equation is d2 u prime d theta square and plus u prime equal to 0, and this equation is very well known to you. Simple harmonic motion, you do this similar kind of thing, d2x dx d2x dt square and plus omega square times x is equal to 0. That is the simple harmonic motion equation. So, you know the solution, and you can write the solution as u prime is equal to some constant a cos omega t, omega is 1 here. So, it will be not t here, theta here. So, cos of theta and minus some theta naught, 2 arbitrary constant, this and this. Okay, you can choose theta equal to 0 in such a way, you can choose the x axis in such a way that this theta naught turns out to be pi, and then you will have u prime is equal to a cos theta with a minus sign, and therefore, u will be what is u? U prime plus this. So, u prime plus that. So, mk divided by L square and plus u prime, and this will be cos a plus a cos theta or minus a cos theta. We will just check minus a cos theta, right. U is equal to u prime plus mk by L square. So, mk by L square is here plus u, right, plus this u prime. U is equal to this plus u prime, and what is u prime? U prime is minus a cos theta. So, it is minus a cos theta, and if you take common, if you take common, you can write this as mk over L square and 1 minus e cos theta, where e is another constant. This is just a constant which is coming in this integration. So, this is another constant in terms of this and other quantities, and this is 1 by r, and this is 1 by r. Therefore, r is L square by mk divided by 1 minus e cos theta. That is what we had told, that by integrations of that r dot theta dot all those things you can get this equation of path. So, you can get it so easily from this equation. So, this is another question. A particle is subjected to a force Fr is equal to minus k by r square. This is the usual inverse square attractive force, but then there is another term minus delta over r cube, with the second term being very small as compared to the first term. So, this is a small perturbation in this inverse square attractive force. Show that the path of the particle is like an ellipse under proper initial conditions, that means the energy should be negative and all that, that proceeds slowly at a constant rate. So, that is the question. So, our equation of orbit in terms of u, we had just derived d2 u d theta square plus u is equal to minus m over L square u square f u. Use this here. So, this will be equal to minus m over L square u square, and then f of u will be minus k u square. So, minus k u square and then minus delta u cube. This is f u. This you can simplify, this will be m k by L square. So, this will be m k by L square here, and this will be plus delta by L square and u here. This delta, then u square and u cube gives you u, and then L square here by this minus is plus. Take this on the left hand side. So, you have d2u d theta square and then plus u, and then you have 1 from here and minus delta by L square here, and I have missed m here. So, m here this and is equal to m k over L square, right. So, if you open this, you will have m times delta, and then u and divide by L square, and u taking common, this is 1 here and minus m delta by L square here, and this quantity is here. And remember, this is a small number, this is a small number. So, write 1 minus m delta over L square is equal to omega square. Define a new constant omega, which is 1 minus m delta by L square. Since delta is very small, close to 0, this quantity is close to 1, omega is close to 1. If delta is 0, then it is just 1. And then this equation is d2u d theta square plus this is omega square and theta, and is equal to m k by L square. This is u. Or d2u d theta square plus omega square u and minus m k by L square is equal to 0. Let us call this quantity omega square u. So, let us call this quantity omega square u minus m k over L square as omega square u prime. So, what I am defining is u prime is equal to u minus m k over omega square L square. So, in that case d2u d theta square, it is same as d2u prime d theta square, this is just a constant, and this bracket here is just omega square u prime. So, my equation becomes d2u prime d theta square and plus this whole bracket, and that whole bracket is omega square u prime and is equal to 0. And this is again your very familiar equation, that simple harmonic motion equation, d2x dt square plus omega square x equal to 0, and you know the solution, x is equal to some a cos omega t, like that. Similarly, here you will have u prime is equal to some constant, then cos of omega times theta, there it is omega t, here it is omega theta. So, omega theta and omega theta minus theta naught or theta plus theta naught, like this. So, these are the two constants of integrations from here, and by properly choosing theta equal to 0, that means properly choosing the x axis you can make this quantity whatever you like, and I will be doing it like a minus a cos omega theta. So, that is u prime. And what is u prime? U prime is this. I want to write u. So, u is equal to this quantity plus u prime, and this quantity is m k over omega square L square and plus u prime. So, it is minus a cos omega theta, and this is 1 by r, remember. This is m k over omega square L square, take this common. So, here it is 1 and then minus omega square L square divided by m k here and this a here and then cos of omega theta. Okay, this is another constant. A is arbitrary constant, depends on the initial condition, what is the energy and what is angular momentum, etc., etc. So, this whole thing is a constant depending on how you have started the motion, and we write it as small e. So, this is m k over omega square L square 1 minus e cos omega theta, and this is u. So, r will be inverse of this omega square L square by m k, and then in the denominator 1 minus e cos omega theta, right. So, you can write this as omega square L square over m k and divided by 1 minus e cos omega theta, or r naught. You can call this whole constant, this is constant omega here that we had defined, and our omega is defined here, and that is a constant, mass delta L square. So, this omega square is constant, L square is constant, m is constant, k is constant, this whole quantity is r naught divided by 1 minus e cos omega theta. This is the equation of the path under this slightly perturbed inverse square attractive force. Now, how it looks like, and remember omega is very close to 1. Omega is very close to 1, we had defined omega here. If delta is very small, if delta is 0, omega is just 1. So, here if delta is 0, what happens? What happens if delta is 0, omega is 1. So, it is 1 here, it is 1 here, it is 1 here, and you get back the original equation r naught divided by 1 minus e cos theta. But now, omega has a value which is slightly different from 1. So, what is the effect on the shape of this path? So, let us see what is the maximum separation of this particle from the origin, and that maximum separation will be again r naught divided by 1 minus e, and that is when this quantity is 1. So, r is maximum, and that is r naught divided by 1 minus e, and that is when cos omega theta is 1. And what are those values of theta? So, omega theta can be, let us say 0, can start from here, then it can be 2 pi, then it can be 4 pi, then it can be 6 pi, and so on. At these values of theta, you have cos omega theta equal to 1, and then r is this. Similarly, r minimum you can calculate, r minimum is r naught divided by 1 plus e, and when this cos of omega theta is minus 1, then this is r min, and cos omega theta minus 1 means omega theta should be pi or 3 pi or 5 pi and so on. What happens to theta? Let us start for this equation. Theta is equal to 0. Next, theta is 2 pi by omega, next 4 pi by omega, next 6 pi by omega, next 8 pi by omega. And omega, I have just erased that, omega is slightly less than 1, right. Omega, you see the expression of that omega square that we have defined, it is slightly less than 1. So, this quantity is slightly more than 2 pi. So, this quantity is slightly more than 2 pi, and wherever at whatever theta this becomes maximum, once again you go slightly more than 2 pi, you will get this next maximum. It is a kind of ellipse, remember it is kind of ellipse, omega is very close to 1, but then if your ellipse started like this is the maximum distance, let us say this is the maximum distance of the particle, and then it goes, normally it should have come back here to become maximum, but now it is becoming maximum here. So, this major axis, similarly this minimum is not at pi, theta pi, this minimum is at pi divided by omega, slightly more. So, minimum is not here, minimum is here. So, this major axis has tilted, and your path will be something of this kind. Here it is turning. So, this is that shift. So, this is R max, and next R max is coming here, very exaggerated figure. Once again R max is here, okay, and next time when it comes, and R min is somewhere here, and next time when it comes, the maximum will be somewhere here. So, see, this was the major axis, then this is the major axis, and then this is the major axis. So, the major axis is turning. So, the whole ellipse is turning, that is the precession. So, if the inverse square force is slightly disturbed, and that slight disturbance is of 1 by r cube type, then the path will be a precessing ellipse. In fact, it is related to the very famous observation of precession of orbit of Mercury around Sun, which was the first test of general theory of relativity. From Newtonian mechanics, we can do all this analysis, we can find the effect of other planets which are there, which is perturbing that inverse square attractive force due to Sun only. So, that precession is explained by this Newtonian theory, but the amount of precession and is very small. It is only, depending on which frame you are talking, it is only a few hundred arc seconds in 1 century, 100 years, and Newtonian mechanics, taking care of other planets and other disturbances, can account of most of it, but some 43 arc second was not explained by this, and that is very well explained by general theory of relativity of Einstein, which is a modification, or which is a totally different theory of gravitation.